I'm now presenting ELENAS, Elementary Neural Architecture Search. The idea behind our work is that neural networks typically rely only on a few key building blocks. You can think of feed-forward, convolution, or also long short-term memory or transformer blocks. On an elementary mathematical level, these building blocks consist of a relatively small number of different operations. For instance, these are basic arithmetic operations for scalars or matrices or nonlinear activation functions. But still, there's a lot of different combinations of these operations. So it's clear that this space is far from being fully explored. Nonetheless, we believe that it includes undiscovered features that are as novel as the cell state of LSTMs or the attention mechanism of transformer-based architectures. This contrasts the current research direction of neural architecture search, since current work in this field mainly focuses on designing neural networks by combining already existing and well-established building blocks. But we, on the other hand, we are searching for these general purpose building blocks, and those building blocks that should then be again utilized as part of neural architectures. And to do so, we propose ELENAS. So let me share my presentation quickly to dive into the inner workings of ELENAS. So we utilize the search strategy PPO, which stands for Proximal Policy Optimization. In this reinforcement learning setting, building blocks are represented as the states. They're encoded as computation graphs, as depicted on the left. Nodes thereby symbolize learnable parameters or latent representations of the building block, and directed edges symbolize the elementary mathematical operations. Each edge of the initial state is of type none, and they are then sequentially being predicted as part of an episode. As part of the building block search space exploration, the reinforcement learning agent processes the state with a graph neural network. The actor then predicts the edge type based on the two node embeddings that the edge connects. This is then the action in the reinforcement learning setting. And the critic predicts the state value based on a globally pooled graph embedding. They are then both stored in the replay buffer to train the agent. And as part of the building block performance estimation, a neural constructor converts the new state to a neural network that is trained on synthetic datasets. These datasets are of increasing level of difficulty and assess the general capabilities of the building blocks in the respective domain. This is then the reward of the reinforcement learning setting. And this is, for instance, a capability of remembering something for a long time lag in the domain of sequential data. And this process is then repeated for every edge in the computation graph. This is then one episode on which the agent is trained on. And the agent thereby incorporates expertise in designing high-performing building blocks with elementary mathematical operations. So empirically, we demonstrate that ELENAS leads to previously unparalleled building blocks that also generalize well. They even transfer well to real-world data when they are stacked together. So they approach or even outperform existing modern neural networks in the specified domain while requiring only a fraction of the learnable parameters. So to conclude, we showed that it is worth further exploring the general search space of elementary mathematical operations to find novel general purpose building blocks that could become of general importance for machine learning practitioners.